15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again, and thank you for joining us on this, the Space Nuts podcast, all about astronomy and space science, episode 215. My name is Andrew Dunkley, and joining me, as always, is Astronomer-at-Large, Fred Watson. Hello, Fred.
Hey, Andrew. How are you going?
I am quite well, sir. How are you?
Yeah, still hobbling around on the new knee. All going well.
Oh, yes.
Yep.
That's good. Not having to go through any MRI machines or, what do you call it? You don't have to worry about airports at the moment, so it's a good time to get it done.
It's off the agenda completely, so there's no worries there. Yeah.
Yes. Now, today, Fred, we're celebrating episode 215 for no reason whatsoever than it is episode 215 by mostly answering audience questions. We've got questions about the Ceres impact crater, dark matter versus dark energy, supernovae, detection of gravitational waves, and questions about the condensed universe. So we're going to tackle all of that today. But before we do, we'd like to make note of a special place just down the road from here, about an hour and a bit's drive from where I live, the Parkes Radio Telescope, which has been officially noted as to be heritage listed, which is something very, very special.
Absolutely right, Andrew. And you normally think of heritage-listed buildings as ones that were, perhaps put up in the early days of colonial Australia, buildings of historical significance, which don't do anything anymore other than usually acting as a museum or something like that. That's what separates the dish, the Parkes Radio Telescope, from most other heritage-listed buildings, because it's still a frontline scientific institution doing leading-edge astronomy and space science. Why has it been heritage listed? Because it is such an icon of Australian science. It was built in 1961. It will celebrate its 60th, is that right? Yeah, 60th birthday next year. But since its construction, and it is huge, it's a marvelous facility. I think it's one of the most beautiful telescopes in the world of any kind. It's this 64-metre dish in the middle of sheep paddocks and some very nice wooded avenues that weren't there when they built it at first, but they are now. That telescope, commissioned back in 1961, immediately started revolutionising our understanding of the universe. In fact, one of its first highlights was the following year, 62, when researchers discovered that our galaxy has a magnetic field which is about 1 million times weaker than the Earth's magnetic field. That's a stunning discovery that needs radio astronomy to do. And then there's a long and distinguished list which you can run down. In fact, one of the things that Parkes is best known for is basically the discovery of pulsars, the discovery of many pulsars. Let me put it that way, because the first pulsars was discovered back in the UK. Pulsars, which are rotating neutron stars, they are very much Parkes' stock in trade. It's also been used to discover quasars, radio loud quasars. There's a note in the list I've got in front of me, which says 1982, researchers using Parkes discover a quasar called Parkes 2000-330, the most distant object in the universe known at the time. And I remember that well, because I was living in Edinburgh then. It was on the eve of me coming to Australia. I was working at the Royal Observatory in Edinburgh, and I got called upon to record an interview about that with BBC Scotland, the discovery of this most distant known object. So I went into the studio, we recorded the interview. They said, it'll be broadcast tomorrow morning. Tomorrow morning came, and Argentina invaded the Falkland Islands. So it just got lost. It never went to air. My first radio story disappeared on the cutting room floor. Just the way
I'm laughing from the journalistic point of view,
yes,
of course.
That's right. Yeah, it's whatever the big story is takes the biscuit.
It is.
And continue to be significant. Of course, the thing that most people remember it for is the TV signals that came from the Apollo 11 moon landing, relayed to a 600 million people worldwide audience back in 1969. And it's still going strong. It is. Yes. And in fact, it's involved with has been involved with some of the Voyager tracking. I think that might have stopped last year, but Voyager 2 was until last year was still being tracked by the Parkes dish in support of the Canberra Deep Space Communication Complex. Great stuff, though. And congratulations, Park.
Yeah, it's fantastic. Good for them. And it was the 118th thing to be heritage listed in Australia.
Oh, that's interesting.
Do you know what the 117th was?
It's probably Andrew Dunkley.
No, it was my first set of golf clubs, and they were heritage listed for being the losingest set of golf clubs in the history of the game.
Yeah, I wasn't far off.
Yeah, no, that's great news about the Parkes radio telescope. It's also within view of the notorious Newell Highway, and it's a bit of a traffic hazard because you'd so much want to look at it.
Yeah,
but you've got to keep your eye on the road. It's, and it's a 100 zone too, which it's a bit scary. Now let's move on to our very first question and see if we can sort something else out for Paddy. He's become a bit of a serial questioner, has Paddy.
G'day, Fred and Andrew. It's Paddy the Roofer from Sydney. Thanks for answering my question the other day, although Fred needs to do some research. Anyway, I thought it might be a great idea, just saying, to maybe have a Space Nuts convention, like where we can all get together, meet up, and say hello. And, it might be possible after all this COVID thing is gone and dusted. I thought it might be a great idea. My partner, Natasha, she said the same thing. And I'd love to bring my telescope and show it off, which I know it's not the biggest one, but it's pretty awesome. But you guys really inspired me to, get into this stuff again from when I was little. And now my kids are starting to get involved, which I think is great. But, so maybe a Space Nuts convention might be an ideal thing in the near future. So anyway, have a great day, have a great weekend, and may the force be with you.
Thank you, Paddy. Commiserations on your small telescope. Natasha must be a very patient woman. Now, a convention. I like the idea of a convention.
It's great, isn't it? And I guess at the moment we are in such an unusual state that we can't really think of things like this. But down the track, Space Nuts Convention, look, it could be a big thing. We could bring along Gregory and the whole caboodle to have a look at, to sing to the Space Nuts conventioneers and just basically catch up and chinwag about what we've been doing. The only thing is, Space Nuts has a global audience, which actually is something I'm very happy about, and never fail to tell people if they ask me about it. And some people,
we might have to go on tour.
Yeah, well, that's right. It might have to be this Australasian version, the version for the Americas, and the European version, and maybe even a Far Eastern version. Who knows? That would be great.
Yeah.
Great suggestion. Thank you.
It's a good idea, Paddy, and Muscat thinks the same thing.
Yeah.
He's made his debut.
No, that's actually one of the peacocks outside that just made that noise.
Oh, is it? Oh, it sounded like a cat.
Yeah, well, Muscat actually is here. He's asleep right next to me, and he's not saying much.
Fair enough. All right.
Paddy,
well, I'm sure he'll make his Space Nuts debut very soon.
Yes, he will, yeah. The reminder that I need to do some research, which I haven't done yet, but I will get to it. We'll track back to find out what it was, and then we'll do it.
Okay. Thanks again, Paddy. Now, we have a question from Richard in regard to the mountains of shimmering crystals in the crater known as Cerealia Tholis at the centre of the Okator crater on Ceres. What is it and how did it happen? This is actually a story that's popped up in the news this week.
Yep.
So he was quick off the mark asking about that one.
Yeah, and thanks for that, Richard. It is a great question. And I don't know whether you'll remember, but the Dawn spacecraft, which was in orbit around Vesta, one of the bigger asteroids in the asteroid belt, then it transferred to Ceres, which is one of the dwarf planets of the solar system. Until 2006, we just considered it to be the biggest asteroid in the main asteroid belt. But it is more or less spherical. That counts it as a dwarf planet. It's not a planet because it hasn't cleared its part of the solar system of other debris, as witnessed by the fact that it's sitting in the middle of the main asteroid belt. But it is a large and interesting world. And as Dawn approached it, we kept seeing these pictures of this crater with bright spots in the middle of it. Really very, very striking. And for a few weeks, the wires were running hot with, this is clearly extraterrestrial intelligence putting signals on in the middle of this crater to welcome us to the dwarf planet Ceres. But it turns out when you get closer to them, they're sort of bright, clearly natural spots of something very, very much lighter than the area around them. As you said, they're in the middle of something called a Carter crater, and basically they've got a name of their own, Cerealia Facula. Facula is something bright, so that sounds okay. It was quickly realized that what we were probably seeing was salts that had perhaps leaked to the surface from what might be a surface ocean. Possibly Ceres has an icy surface, and all of this was speculation at the time. But now there's been a close analysis from the final orbits of Dawn, where it was only 30 kilometers above the surface, of the chemical composition of these bright spots. Most of it is sodium carbonate, which was kind of known right from the beginning. So it's brine, basically. This is, something that's left behind when salty, really, really salty water evaporates. But what's exciting is that the scientists, and I can't remember where this group is based. Some of them are in New Zealand. And some are in somewhere, JPL. Okay. Jet Propulsion Laboratory at the California Institute of Technology, as you might expect, because that's where Dawn was operated from. However, what I was going to say was the exciting bit is that this, as well as the sodium carbonate, there is something called hydrohalite, or sometimes known as hydrated sodium chloride. And that's basically right on top of this white patch of stuff. The reason why that's notable is it's the first time this stuff, this hydrohalite, has been found anywhere beyond the Earth. And one of the lead scientists says it's not stable on the surface of Ceres. It would dehydrate, he says, within, and he's saying this generously, 100 years, but it could be even faster than that. And so what that suggests is that what we've got here is an ocean world, which is kind of a bit reminiscent of some of the moons of the outer planets. Possibly not a global ocean, but certainly with reservoirs of briny water underneath the surface, which is leaking out through this crater floor, which is probably where the crust is fairly weak, because that's been clouted by a crater, I think they estimate about 20 million years ago. So a fairly recent crater, but even more recent seepage coming through from beneath. That's really interesting discovery. And so it marks Ceres out as one of the really interesting places because it's got water, liquid water probably underneath its surface.
So yet another world within our solar system that could potentially harbour life. Maybe could be.
It could be. The scientist, and I might have called this scientist a him a minute ago, but it's actually Carol Raymond is her name. She says it's unlikely that the ocean, if it was thicker and there was lots of energy around, maybe you could have life forming. But she says it's unlikely that persisted over sufficient time to allow the emergence of life.
Right.
And so the suggestion is that it might have been a bacterium that's come from somewhere else that would have landed in there and flourished. But really, there's not a great hope for life having formed there.
But the fact that there's something that's been found that hasn't otherwise been seen except on Earth is quite a discovery.
Right. It's extraordinary, isn't it? That's a big find.
Huge. Okay. Thank you, Richard, for the question. Hopefully that covers it for you. And we are going to continue to answer questions here on Space Nuts, episode 215 with Andrew Dunkley and Fred Watson.
0G, and I feel fine.
Space Nuts.
Thanks again to our patrons for supporting this podcast financially, whether you do that through patreon.com or Supercast or through the Acast option on our official website, spacenutspodcast.com. It is purely optional, but it is so heartwarming to have the kind of support we get. And it is certainly something that we greatly appreciate. If you would like to do that, you can log on to your favourite patron website, whether it's patreon.com/spacenuts or Supercast, and sign up for whatever option you want. Supercast is offering combination deals, so you can have 2 or 3 podcasts for the price of 2 or 3 podcasts. But, it's an option to consider. So have a look at it. You can get all the details from the website, of course. Now, Fred, let's move on to our next question. This comes from Jeremy in England.
Hello, it's Jeremy here from England. Are dark matter and dark energy contradictory? Dark matter is supposed to be drawing everything together to hold galaxies together. But then on the other hand, there's dark energy, which is causing these galaxies to separate even at an accelerating pace. It just doesn't seem to make sense to a simple layman. I hope you can give us an answer on that one. Thank you. Take care. Bye.
You take care too, Jeremy. Thank you very much for the question. Yes, the subject that everybody wants the answer for, that nobody can find the answer for because half of it we don't even understand.
Yeah, and to be honest, I absolutely sympathise with Jeremy because these are two things that have similar names, dark matter and dark energy, which we bandy around. There are names that we just flit around willy-nilly without really giving much explanation. And they do seem to be contradictory. They seem to work in opposite ways. But they are, the main thing to remember is that they're really quite different in the what might be called their phenomenological appearance. In other words, the things that they produce. Dark energy is the easiest one. Dark matter is the easiest one to deal with. That the story goes back to 1933 with Fritz Zwicky discovering the cluster of galaxies in Coma Berenices, the northern constellation of Berenice's Hare. A huge cluster of galaxies there whose velocities he could measure. And when he measured them, he realized that they were all moving too fast for gravity to hold the cluster together. It should have just evaporated, 10 billion years ago because they're moving so fast. So that was the first hint that maybe there is something that we can't see that has a gravitational attraction that would hold a cluster together. And of course, followed up by in the 70s, the work of both Ken Freeman here in Australia, Vera Rubin in the United States, that demonstrated that galaxies are rotating too fast for what we can see to hold them together. So that's when it sort of gets interesting, though, because from the observations that those scientists made, you can deduce that dark matter is clumpy, that it is something that concentrates where normal matter is. So it is something really quite specific to normal matter, in some ways attached to it. And we now believe that the reason for that is that the dark matter sort of framework was laid down very early in the history of the universe, and the hydrogen of the universe, which was probably spread fairly evenly in the young universe, gravitated towards the dark matter scaffolding, if I can put it that way, and formed galaxies. So the galaxies are there because the dark matter was there. But we know from many, many different kinds of observations that dark matter is not something that pervades the universe uniformly. It is basically, there's a structure of this stuff which is revealed by galaxies, exactly as I think it was Matthew Collis, one of my colleagues at the Australian National University, who described galaxies as beacons of light on hills of dark matter, because the galaxies are the ones that have lit up because of the fusion of hydrogen in stars. So we see the galaxies, we don't see the dark matter. So that is a structure. So whatever it is, dark matter, and it is almost certainly some sort of subatomic species that we haven't recognized yet, maybe even a whole range of them, like we have with the normal subatomic species. It's something that has gravity but really doesn't interact in any other way with normal matter. And we shouldn't be surprised at that, because there are particles of normal matter that behave almost like that, and we'll talk about them a bit later in this episode of the podcast. That's neutrinos. Neutrinos charge straight through the Earth. They hardly interact with it at all, but they do interact with material enough that we can detect them and know that they're there. That's the drawback with dark matter. It's kind of one step further. It really does not have any effect on normal matter except through gravity. And just one other thing before I leave dark matter. There is always the possibility, and I know there's one listener to this podcast who is pursuing a PhD research program in exactly this topic. There's always the possibility that we've got things wrong, that maybe dark matter is not there, but our understanding of the way gravity works is flawed. Most scientists don't accept that for pretty good reasons, because if you do accept that, you've got to face other problems as well. But MOND, the modified Newtonian dynamics theory proposed by Mordechai Milgrom back in the 1980s, is still a subject of active research, just in case we've got the dark matter thing wrong. Now, that might seem a bit vague and hand-waving, but it gets even more so when you turn to dark energy, because that's a property of the universe as a whole. And whatever it is probably uniform within the universe. And it goes back to 1998 when these two groups of scientists, one in the USA, one here in Australia, actually recognized that the expansion of the universe is accelerating. And that was put down to this phenomenon of dark energy, which essentially is supposed to drive the accelerated expansion and give us this phenomenon of everything, pushing away from everything else at a greater and greater speed as the universe evolves. What is it? Well, two possibilities. Once again, we're only talking about the way the phenomenon manifests itself. It could be something we call the cosmological constant, which is something that it's named that because it's a term that Einstein put into his equations of relativity. The cosmological constant suggests that whatever this dark energy is, it's proportional to the volume of space that it's in. So as the volume of space expands, the dark energy gets bigger and pushes it to expand even further. That's probably the way it behaves. But there are other suggestions that say perhaps it only switched on a few billion years ago. Perhaps it's some new force of physics that we haven't recognized before. Maybe something called quintessence, which is a name that's bandied around as well. These are still ideas. There is no firm, understanding of really what it's about. So I think the solution of the dark energy problem is more years down the track than the solution of the dark matter problem. Once again, Jeremy, I hope that's clarified this, because it is a complex universe that we live in, and it's got these various attributes which astronomers are not clever in naming. I think dark matter and dark energy are not good names for these things, because they sound too similar, and exactly as you've said, they sound as though they do the opposite thing. But actually, they're quite...
Well, if and when we solve both of them, maybe they will then come up with a proper name for them.
Maybe that's right. Maybe we will have a name for them, and that's a very good point. It could be the front runners for dark matter are particles called neutrinos or axions, and so we might, if ever they're discovered, we might talk about them rather than dark matter in a vague way. Because we don't talk about visible matter. We do. We've got a name for that as well. It's called baryonic matter. Baryonic matter is normal matter. So maybe antibaryonic matter is what we're dealing with.
Oh, boy. That's another murky little area to walk down, I think. All right. Jeremy, thanks for the question. A very thought-provoking consideration indeed. Now let's go straight to our next question. This one comes from Mark.
Hey, Fred and Andrew. Love your show. This is Mark. Question for you. What happened with the supernova 1987A, where neutrinos were detected days, maybe, before the visible light? Was there a speed limit problem here? Hey, this is an interesting one. You guys take care. Thanks again for everything. Bye.
They're all interesting ones, I find, Fred. But thank you, Mark. Supernova 1987A. I'm guessing we just want to know what happened.
That's right. So that is exactly what happened. It wasn't actually days between the neutrino pulse and the visible light pulse arriving. It was approximately 2 or 3 hours. So it was a matter of hours. And it doesn't come about because of anything to do with the speed of light. The neutrinos effectively travel at the speed of light, and so does the light pulse, naturally. What you're seeing here is the effect of... it's the mechanism by which the light pulse is caused. So what you've got is the core collapse, the collapse of the core of this star, which turns into then a neutron star. That collapse instantaneously produces a pulse of neutrinos. And that's why they arrive first, because... you don't get visible light until the shock wave of the collapse reaches the surface of the star. And that's when the thing blazes into bright emission. It's all about the shock wave. So that shock wave taking a couple of hours to get from the collapse of the core itself. Remember, the core is only, by the time it's collapsed, it's only 10 to 20 kilometers across. That it takes a couple of hours for that shockwave to reach what was the surface of the star and to light up basically what's going on. So it is all about shockwaves. And actually, the subsequent evolution of supernova 1987A is all about shockwaves as well. The curious things that we see now with the Hubble Space Telescope, showing this sort of ring of bright emission, that's to do with the shockwave reaching some of the debris that was shed by the star earlier in its degeneration, as it sort of, basically became unstable before it actually turned into a supernova. So no hocus pocus with the speed of light here. It's all about the physics of what causes those emissions.
Okay. I saw a documentary recently, and I can't remember the numbers, but they were talking about how long it took a photon from within our own sun to get to the surface to then do the trip to Earth and beyond, and it was some weird amount of time. So that the light is created, but it's deep within the star, and it takes I don't know if it was hours or days or whatever it was to get out.
It's a million years, Andrew.
A million years. There you go. It was a long time. I just couldn't remember what it was.
Yeah, it's crazy stuff.
It's
and that's
incredible, isn't it?
It's because of the density of the sun. You've got, a photon is emitted and then it's immediately reabsorbed to form another part of the nuclear reaction, then re-emitted. And this scattering process, which is basically what it is, takes, a million years.
Wow. Okay. And, everyone thinks of the speed of light as something pretty quick and it just gets out there, but it doesn't.
Not always.
The stars are such powerful entities that they can hold back the light, bounce it around, and keep it there for a million years. Well, you're not going anywhere, Sonny Jim. I am the sun.
Yes.
Maybe we were right to worship it. Anyway, thanks very much for your question, Mark. Hope we've answered the query regarding Supernova 1987A. You're listening to the Space Nuts podcast, episode 215, with Andrew Dunkley and, of course, Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, there are many, many ways to listen to the Space Nuts podcast. You can listen on your favourite podcast distributor, which is any number of podcast distributors. I think we're on just about all of them, particularly the big name ones. But you can also listen via YouTube. So all you have to do is do a search in YouTube for Space Nuts podcast, and you can download us there. All our episodes are on YouTube. And, where else? Just about anywhere. If you do a search for Space Nuts podcast, you will find us, I'm sure. There was also a movie called Space Nuts. Don't get confused. They're just as weird as we are, but not the same kind of weird, I venture to say. Now, Fred, let's move on to our next question. This comes from an unknown entity. We will call him Dark Energy because we don't know anything about him, but he does have a question for us.
My question is, how can you measure the expansion of space-time in gravity if you're in space-time? So if you have a ruler that measures 10 centimeters and it's expanded by gravity to 15 centimeters, it will still measure 10 centimeters. Similarly, with the space interferometer, the arm of the interferometer may be 4 kilometers long, and that's measured with a beam of light. But surely the measurement expands the space-time, and so would remain the same length by any form of measurement that's in the same frame of reference. So my question is, if we were stretched out as we were falling into a black hole, how would we know?
Now, that is a very good question. You might have to re-explain some of what he's asking, Fred, because the audio quality was a little bit iffy in places.
Yeah.
But, measuring space-time, I suppose, is the essence of the question.
Yes, it is. And let me just address specifically the gravitational wave part of that question. So what we've got with the LIGO detector, the Large Interferometric Gravitational Wave Observatory, and there are 2 of these things. There are 2 4-kilometer long tubes, I guess, at right angles to each other. Excuse me, frog in the throat there. This is each of these 2 detectors. They're opposite ends of the United States. They've got the same structure. They have 2 4-kilometer long tubes, which are evacuated. They're in a vacuum, and they're at 90 degrees to each other. And this forms what's called an interferometer. So you send a beam of light down one arm, basically you start off with one beam of light, you split it into 2, send one half down one arm, the other half down the other arm at right angles to it, and then they come back and they're recombined. and that lets the light waves interfere, which basically causes darkness. Actually, if the two arms are exactly the same length, they cancel out. And so what you can then do is, if a gravitational wave passes through, there is a difference between the lengths of these two arms, and that reveals itself by the light appearing. And that's how the thing works in a nutshell. So you could argue, apply exactly this same argument, that the distortion of space as a gravitational wave passes through one of the arms of the interferometer, it changes the length of the interferometer from 4 kilometers to 4 plus or minus a gazillionth part of actually, it's about 10,000, 1/10,000th of the diameter of a proton is the change in it. It's extraordinary stuff.
Super fraction.
That's right. So why, but as our questioner says, if you've got a ruler that measures 10 centimeters and it's expanded by 15 centimeters, it will still measure 10 centimeters. And that is true, because the ruler in this case is the wavelength of the light being used, the laser light. And that does change too as the gravitational wave passes through. That changes. But the way that LIGO works is the fact that you've got the two beams at right angles, and as a gravitational wave passes through, one stretches as the other shrinks, and it's actually the difference between those two lengths that is the characteristic thing that you measure that tells you that a gravitational wave has passed through, even though the waves of light themselves are being affected by the gravitational wave. It's the difference between the two path lengths. So that's kind of, explains the conundrum with the LIGO. The thing about falling into a black hole, the reason why you would know that you are falling into a black hole is that the expansion of space-time is different from your head, between your head and your feet, or in this case, it's a contraction of them. So that means you basically get spaghettified. So there is a difference, and it's a bit like the path difference between the two arms of the interferometer. It's the difference between what's happening at your feet and what's happening at your head. That's how you'd know you'd fallen into a black hole, because it would be very uncomfortable.
Okay. All right. I'm confused, but hopefully our unknown questioner has understood the answer, Fred.
Yeah, I hope I did too.
Okay. No, thanks for the question. And a reminder too, if you do send us an audio question, please remember to tell us who you are, because we like to know. And it also helps to identify the person involved and makes it easier for us. But, no disrespect. It's all cool. But thanks for the question. We appreciate it. We've got one more we can squeeze in before the end of this week's episode, Fred. This one is one that came in via email from Richard Milligan. A short, sweet question, which I'm sure will have a short, sweet answer. Why didn't the condensed universe form a black hole but instead expanded? Thank you, Richard. Interesting question. I'm not if the condensed universe was pre-black holes, then the conditions may not have been right to produce a black hole under those circumstances, I imagine.
There you are. You've answered it.
Oh, have I?
No. So what we believe, by believe I mean this is what relativity theory tells us, that the universe began with a singularity. A single point, and that effectively is a black hole. It started as a black hole, but for some reason it exploded. Maybe an instability. We really don't know much about the mechanism of what caused that explosion, what caused the expansion and the release of energy that we still see today with the expanding universe. So it is. Rich describes it as a condensed universe, and that condensed universe is a singularity, a single point, which is the definition of a black hole, except it's got infinite density. And maybe the early universe had infinite density too. Some people have thought in terms of the universe having its own event horizon in much the same way a black hole would, and that everything is within the event horizon. I can't get my head around that, I have to say, but that once again underlines the parallel between a black hole and the universe as a whole.
Okay. Thank you. No, I mean, the thought of the whole, everything starting as a black hole, I suppose what prompted the question in the first place. And, how did it sort of go beyond that and not collapse in on itself? And, we never existed at all. Well, obviously we do. But that's probably one of the greatest mysteries of the universe. Why are we here? How are we here?
Maybe so. Richard, no, not Richard Dawkins. God, his name's gone. That's ridiculous. It's what happens when you get old.
We'll call him Spike. Richard Milligan.
No. I'm talking about one of the great physicists, Roger Penrose.
Okay.
Okay, Penrose's theory is exactly this, that the universe starts off as a black hole, becomes unstable, expands. As it expands, it forms other black holes, and eventually they grow big enough that they too turn into new universes. So it's, that cyclic kind of Penrose idea is maybe a parallel with what Richard Milligan is suggesting.
Okay. Very good.
And I also like this comment after the question, Andrew, which you didn't read out.
Which I don't have in front of me.
Let me have it in front of you for you. Richard says, love the show, Rich, which is nice. But he also says, P.S. Mr. Peck is already a giant of Australian broadcasting. And that's Marty's rooster.
Yes, that's probably true. It took him one go to be more famous than me. But it wouldn't be difficult. It would not be difficult. Yes.
Marty's suggesting that he might just be a one-hit wonder.
It's a distinct possibility in this game, I must say. Have we got a photo yet? I'm sure we'll be asked again.
Yeah, there's one on its way.
Yes, that's what they all say. Checks in the mail. Thanks for the question, Richard. Really appreciate it, and the good humour that goes along with it. Thanks to everybody who asked questions. We didn't get to absolutely everybody. We will add more questions to the mix in future episodes. And if you would like to ask an audio question, go to our website, spacenutspodcast.com, and click on the AMA tab. And if you've got a device with a microphone built in, such as a smartphone, a tablet, or a laptop computer, it's as easy as pressing the record button, and away you go. Don't forget to tell us who you are. And that wraps us up for another week. Fred, thank you so much. We've had our challenges today, technically speaking, so a little bit messy in the middle, but with some clever editing, I'm sure we can hide all that.
I hope so. Thanks very much, Andrew. Good to talk, and we'll speak again soon.
We will indeed. That's Fred Watson, Astronomer-at-Large, part of the team here on the Space Nuts podcast. Thank you for listening. Thank you for your support. Looking forward to your company in the next episode of the Space Nuts podcast.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.